Dynamic Coordinate Reference Systems. Hello, I am Roger Lott of the IOGP Geomatics Committee. Here is the movement of the Earth's tectonic plates over the past 100 million years. In this presentation, I will explain how this tectonic motion impacts positioning and spatial data management today. The various tectonic plates move at different speeds in different directions, and their movement of a few centimeters a year continues. We are zooming in to consider this plate movement in a human timescale. You can see a large-scale map showing a road junction with nearby buildings and lampposts. If you look to the left of the map, you can see the coordinates of one of these lampposts. The coordinates in black are reference to the CRS used by the GPS satellite navigation system WGS-84. WGS-84 is an Earth-fixed coordinate reference system, that is, it is fixed to the Earth as a whole rather than to any point on the surface of the Earth. From January 1994, WGS-84 has been kept aligned with Geodetic Science's Best Global CRS, the ITRF, to within a few centimeters. The coordinates in blue are referenced to GDA-94, an Australian coordinate reference system which is fixed to and moves along with the Australian landmass. GDA-94 was defined to be coincident with ITRF on the 1st of January 1994. So, in January 1994, because both GDA-94 and WGS-84 were coincident with the ITRF, the WGS-84 coordinates of the lamppost were the same as those in GDA-94. Now, as the years roll by, we can see the Australian plate and everything on it moving north-northeastwards at about 7.5 centimeters per year. The blue plate-fixed GDA-94 coordinates do not change. The Earth-fixed WGS-84 coordinates, now shown in red, are changing with time. Now this seems utterly bizarre. We know that Australia is moving, but the plate-fixed coordinates do not change. Meanwhile, the Earth-fixed coordinates are changing with time. Why is this? The perspective is that of you and me, stationary observers on the surface of the Earth. We do not feel the plate motion, but we are moving with the tectonic plate, along with the street, the lamppost and the plate-fixed coordinate reference system. Because they are all moving with us, we see no change to the GDA-94 coordinates. So we say that GDA-94 is a static coordinate reference system. But the tectonic plate and everything on it is moving slowly through the Earth-fixed WGS-84 coordinate space. The coordinates change, to us they seem dynamic, and so we say that WGS-84 is a dynamic coordinate reference system. So what does this mean? Coordinates referenced to a dynamic CRS such as WGS-84 are ambiguous unless they are qualified by a date. This is given as a coordinate epoch, a decimal number in the Gregorian calendar usually given to 2 decimal places. Coordinate epoch is an attribute of the coordinates, not of the CRS. But the CRS's description of whether it is dynamic or static informs us as to whether coordinate epoch is required. Coordinates can be converted to another coordinate epoch to compensate for tectonic plate motion without any other properties of the dataset altering, and because of this, coordinate epoch is unlike other time-related metadata. It needs to be treated separately. Now this illustrates a problem that has emerged with coordinate reference systems. WGS-84 has been treated as if it were a static CRS because coordinate epoch has been ignored. This is not a problem at regional scales and low accuracies, but without correction it may not be tolerable for higher accuracy applications. What do we mean by high accuracy? We can define it as positioning in a dynamic coordinate reference system where the tectonic plate movement accumulated over the lifetime of the project cannot be ignored. Assuming a project life of say 30 to 40 years, and then depending upon the rate of movement of the relevant tectonic plate, the threshold for ignoring plate movement is between 1 and 3 meters. So if positioning errors of 1 to 3 meters are not significant, you can ignore time-dependent corrections of coordinates referenced to a dynamic CRS. But if you need accuracies of better than 3 meters, or are mapping at scales of larger than 1 to 10,000, then you must either use a static CRS or use a dynamic CRS and account for the change of coordinates with time. So why is this important? Let us have a look at an example using our earlier clip where you can now see two lampposts across the road from each other. The distance between them is calculated from their coordinates. You can see that in the static coordinate reference system GDA94, shown in blue, this distance never changes with time. The distance is also correct in the dynamic coordinate reference system WGS84, but only if you have the coordinates of both lampposts at the same coordinate epoch. It doesn't matter what that coordinate epoch is, could be 1994 in purple, or in 2020 in black, or at any other date. But, as shown in red, if you use the dynamic coordinate reference system for positioning objects at different times and you ignore the change of coordinates with time, then the distance you calculate between the two locations will be in error. It will be in error by the amount of plate movement between the two dates. So remember, when dynamic coordinate reference systems are being used, geometric calculations are valid only when all coordinates have the same coordinate epoch. Ignoring this could have significant consequences. The oil industry has an expensive example when the bridge to be installed between an offshore platform built in the 1990s and an adjacent platform installed 20 years later did not fit. The old platform had been accurately positioned in WGS84. Coordinates of the new proposed location were calculated, and the new platform installed at these coordinates. But during the installation, a surveyor using distance measuring equipment on the old platform claimed that the new platform was mispositioned. The surveyor on the installation barge insisted the new platform was within tolerance of the specified coordinates. Eventually, the argument was settled by an engineer using GPS on his mobile phone to confirm that the new platform had been correctly located. But, when the prefabricated bridge was brought out to be installed, it did not fit. It did not fit because the WGS84 coordinates on the old platform had not been corrected for 20 years of tectonic plate movement. With the downtime of the installation spread whilst the surveyors argued, and the subsequent delays to production, the cost of this incident ran into millions. Now let us consider some other aspects of dynamic coordinate reference systems. CRSs based on different geodetic datums can be related to each other through a 7-parameter Helmut transformation between two geocentric Cartesian systems. This applies when the two CRSs are static. But when one CRS is static and the other is dynamic, or when both CRSs are dynamic, as the coordinate reference systems move relative to each other, the transformation parameter values change with time. This requires a modification to the transformation method to include time dependency. So, for dynamic CRSs, software support for time-dependent transformation methods is essential. The discussion we have been having so far has been about the slow but continuous movement of the Earth's tectonic plates and its effect on coordinates. But the coordinates of the surface of our dynamic Earth are also changed by occasional catastrophic events such as earthquake and volcanic eruption, or by subsidence caused by human activities such as mining and water extraction. The coordinate changes resulting from these events cannot be described through Helmut transformations. Instead, they are described through deformation models or velocity grids, implemented as so-called point motion operations. These point motion operations are similar to coordinate transformations, but operate within a coordinate reference system rather than between two different coordinate reference systems. The trend is for future geodetic reference systems to have a velocity grid, so in addition to time-dependent Helmut transformations, software supporting dynamic coordinate reference systems should also be able to apply point motion operation methods. If I go back to our earlier problem of GDA94 now being significantly offset from GPS satellite coordinates through 2 decades of accumulated tectonic motion, Australia has fixed this by introducing GDA 2020. GDA 2020 will be coincident with ITRF in January 2020, so currently, for most practical purposes, coordinates referenced to GDA 2020 and to WGS84 may be considered to be insignificantly different from each other. But while this assumption of equality between them is valid today, it will become increasingly inaccurate in the future. Because tectonic plate motion continues, in another 20 years GDA 2020 will have the same 1.5 meter offset from ITRF and from satellite navigation systems as we see today with GDA 94. If static CRSs are to be aligned with dynamic CRSs used for satellite navigation, they will always require periodic update. Let me end with another reminder of the importance of understanding dynamic CRSs. To illustrate it, I will make the somewhat unlikely assumption of two cars using satellite positioning for in-car navigation, but without using any other inputs. The red car uses standalone GPS positioning in the GPS Dynamic Coordinate Reference System WGS84. The green car is also using GPS positioning, but using more accurate relative positioning techniques through the National Continuously Operating Reference System CORS. This makes time-dependent corrections and then delivers locations in the plate-fixed static CRS GDA 2020. Today, when the two CRSs are coincident, there is no problem, but for high accuracy using a dynamic CRS, corrections to the dynamic CRS coordinates for tectonic plate motion must be applied. So, if you want to avoid a car crash, use dynamic coordinate reference systems with care. If you would like further information on dynamic coordinate reference systems or on transformation methods between dynamic coordinate reference systems, it is available in IOGP Geomatics Guidance Notes. IOGP publication 37325 adds more detail to that given in this overview. The application of time-dependent coordinate transformations to the US Gulf of Mexico is included in IOGP publication 37326. Formula and examples for time-dependent coordinate operation methods are documented in the EPSG Dataset Support Guidance Note 7 Part 2. These guidance notes are available through the IOGP website, the address of which you can see here. Then go to the IOGP bookstore.